it that you have the best possible chance to do that. What do you want me to do? Cook up some dizzy experiment where you're trying to figure out how the electron jumps around in the Bohr model of the hydrogen atom? The hell with that. Redox chemistry, Bronsted-Lowry acid-base chemistry. The two most important categories of reactions which take place in water solution by far. So the experiment to which I refer is assignment 5, part 1. Remember these fundamental redox investigations? You began that by looking at a film, a pre-lab video. In that pre-lab video, you viewed a presentation by a very famous actor. You remember who that actor was? One pre-lab video on redox, another pre-lab video on acid-base chemistry. Because it's tough stuff, but it's very important stuff. And I know you're not getting any support in 45 from lecture. So I'm trying to give you that support so you can get at those assignments in a beneficial fashion. In any case, all of this chit-chat is to remind you that you have had some experience with hydrated iron plus 3, and if you recall from your work that you did in 45L, you would have seen that this is in fact a pale violet stuff. So now, after all this chat, we look at these two ionization equilibria, we look at the K values for these two ionization equilibria, we remember that this solution is fairly dilute. We keep in mind that ionization extent depends on dilution factor and K value. So that I can ask you the question, if we were to prepare 100th molar ferric nitrate and ask you to observe it, would you see a pale violet color? If you don't see a pale violet color, what color do you think you'd see?
Blue.
Clear?
Blue.
Clear is not a color. Clear refers to transparency.
Blue.
I don't fault you for that, but any chemistry teacher who uses clear to refer to color doesn't know what the hell he's doing. Which clear means transparent to light, like strawberry Kool-Aid, which is quite clear. Is that clear? How about that? What color do you think you'll see for this solution if it does not appear to be yellow-brown? I mean, pardon me, I gave away the answer. If it does not appear to be pale violet, it'll be yellow-brown. It is yellow-brown. Because in this solution, the molarities of these two species are substantial. Is that surprising when you see that this K value is only 8 times bigger than this K value. Remember when we looked at the comparison of Ka1, Ka2 for polyprotic molecular acid where the parent acid is weak? Oh, the difference in the K values was 1,000,000 at least. Now we're looking at K values which are quite close to each other. What does that mean? Do you think that means that the second ionization equilibrium goes to a substantial extent in this system?
Yes.
You're damn right that's what it means. And yellow-brown is a more intense deep color than pale violet. That's why you see this solution showing a yellow-brown coloration rather than pale violet. And now we get to the fun part. How do we get the hydronium ion molarity for this solution? After having recognized that this thing goes to a substantial extent in addition to this thing, because now this is an unknown, its molarity. Molarity of this is an unknown, that's what we want to find out. The molarity of this is an unknown, and finally the molarity of this is unknown. How many unknowns we got? 4. How many equations we got? 2. So far. Can we solve this puzzle at this stage of the game? 4 unknowns, 2 equations. Can we calculate the hydronium ion molarity? Hell no. What do we got to do? You learned this in algebra class. we've got to develop at least 2 more simultaneous independent equations which consist of the same set of unknowns. Then we can solve. And so we proceed, recognizing that one of the considerations we need, we've already made. It's called material balance. So I have written the material balance equation for dissolved iron. That means iron plus 3, quote unquote, plus 2, quote unquote, and plus 1, quote unquote.
If the reaction you wrote, where is extra nitrogen coming from?
Where is what?
If you have iron plus H2O to H3O.
This? That's what you're asking? Remember what these formulas represent?
Okay. Because it's
So I invented some abbreviational references for my convenience and to save some of teacher's favorite weapon. That's a true conservative. But I'll not go any further with politics at this stage of the game. Now then, this means I can express the molarity of any one of these forms of dissolved iron in terms of the other 2. If, for example, I want to express or make reference to the molarity of iron plus 3, quote unquote, then I'll recognize that's equal to 0.010 minus the molarity of this minus the molarity of that. But we still need one more equation. And we get that from charge balance, which we have reminded you about earlier on, but now we're in fact going to put it to use. So straight away, remember, a charge balance is based on the principle of electroneutrality. It is utterly impossible to get a bulk system of ions of one charge type, all positives or all negatives. In fact, it's utterly impossible to get a bulk system, that means a large system, which contains an imbalance of charge. Such a system is totally unstable. Story. They've told you this before, I'll tell you again. Way back when I started here as a teaching assistant, because I have already told you I did my PhD here at UF. When I started here as a teaching assistant in 1967, where you were all on board, waiting to come here, okay? I had a student in laboratory who, like you, this term, assignment 2, was faced with the task of doing the flame test for sodium ion. And he went to the side shelf and saw all these solutions containing sodium ion, or solids containing sodium ion, but they also contain an anion, like sodium chloride or sodium chloride solution, sodium nitrate solution. And he came back to me and said, I can't find this bottle that's just got sodium ions in it. So I said, well, I'll let this poor soul stew about for a couple more minutes, which he did. And then I brought him back to me and told him a story. I said, how do we make sodium ions? He knew this. You get sodium atoms to react to lose an electron. Ionization energy is the energy requirement, the energy bill for the process. I said, but you can't run sodium to sodium ion plus electron as a reaction all by itself. You can do this in an ionization chamber as long as you keep the energy pumped into it. But as soon as you take away the energy supplication, what happens? The electron jumps back to the sodium ion and reconverts the sodium atom. I said, bear in mind, if sodium could be converted to sodium ion and electron, and the sodium ion could be extracted from the system as a stable product, then so could the electron. And I said, hey, if I could do that, I'd run around ionizing a bunch of metal atoms into positive ions, and I'd collect the electrons. I'd put them in bottles. And I'd open up a store, Horvath's Electron Store. And then I'd sell you a bottle of electrons. You know, electrons are really tiny. You know, a bottle of electrons this big, wow, you'd have one hell of a bunch of electrons. And I'd say, go home, go to the socket on the wall, get out a funnel, stick the funnel in the socket, open up the bottle of electrons, pour in the electrons, and then watch the television televise, listen to the radio radiate, and call up GRU and tell them to go to hell. You don't need them anymore. Unfortunately, this cannot be achieved. I can't get this bottle of electrons. So, resolutely, he gathered himself together and accepted the recognition that he had to use something like sodium chloride to do the sodium ion flame test. Point. Total moles positive charge in a bulk chemical system must equal total moles negative charge. That's the only way the system can be electrically neutral, and from that recognition we write charge balance relationships. For our iron nitrate solution, here is the charge balance relationship. 3 times the molarity of hydrated iron plus 3, plus twice the molarity of hydrated iron plus 2, plus the molarity of iron plus the molarity of hydronium ion. Those are all the positive things in the pot. Equals molarity of nitrate ion plus hydroxide ion molarity. These are all the negative ions in the pot, and that's equal to 0.030. Now comes the fun question. How many of you recognize where this equation came from? How many of you would have been able to write this equation had I not given it to you and I said, write the charge balance equation for this system? Most of you would have said, what the hell? I can't do that. But it's easy. Now let's show you why it's easy. One molar calcium chloride solution. A simple solution. Tell me, for this simple solution, what are the principal species? Let's consider charge balance just for principal species in this system. Tell me the principal species. I write them down. Calcium ion. Chloride ion. Water. That's it. In writing a charge balance equation, will we ever include the formula for a material like water? Why not? It's a molecule. It has no charge. Okay? Now tell me. In this solution, what is the calcium ion molarity? In this solution, what is the calcium ion molarity? In this solution, what is the chloride ion molarity? Wonderful. That was really hard, wasn't it? Now, here comes the real tough question. If I want to write an equation, a charge balance equation, between the principal positive ion species in this system with the principal negative ion species in this system, which we have recognized to be calcium ion and chloride ion respectively, what do I have to do to 1? What do I have to do to 1 to make it equal to 2? Multiply by 2. How about that? Is this not true? Is this not true? It is true, isn't it? Twice the calcium ion molarity, which is 1 molar, is equal to the chloride ion molarity, which is 2 molar. Done. So how did I get this? First, I recognized what all the charged species are that are in the system. That 2045 junk. So, a consequence of what we were just mentioning is, back to this system, because for this system, remember when I wrote up there the question mark indicating the possibility of other principal species? Because in this system, if this reaction also goes substantially, which it does, then in this system we also have this as a principal species and this. And you would not have known that by just the label on the bottle. You would have had to pay attention to this chemistry to know that. So now I can ask the question, as far as principal species are concerned for the aluminum sulfate solution, do you think this is or is not a principal species? Tell me. Remember, this is a weaker acid than acetic acid, isn't it? And in 10th molar acetic acid, we've done a lot of calculations with acetic acid solution. Do you have any gee whiz remembrance of to what extent acetic acid ionizes in 10th molar acetic acid? How much? 0.4%? That's 1 molar acetic acid. So we're going to have to make a correction. In 10th molar acetic acid ionizes about 1%. My memory is right, it's 1.3%. This is a weaker acid than acetic acid. And the parent molarity is 0.1 molar. So I repeat the question, by analogy to the chemistry of acetic acid, is this or is this not a principal species in this system? It is not. You think I'll ask questions like this on the next quiz? You're damn right. Because in answering questions like this, you will tell me whether or not you understand what the heck is going on. And that's what we want. Now then, beside this is a principal species, what else? Well, water, of course, but we're trying to get a charge balance, so we'll forget water. What's the other principal species? Sulfate ion. Goody. So I'll ask right now, give me the molarity for sulfate ion in this solution. What is it?
0.3.
What is it?
0.3.
How about that? I finally got that 0.30. I told you folks, if I made you give me $1 every time you violated significant figure considerations, I'd have a bushel of money probably at the end of one day. And then I would make you all a promise. With this bushel of money, if you from this day forward make no further significant figure violations, I'll throw us a nice beer and pizza party with the money that I have gotten from you. How's that? But first you have to prove you don't violate significant figure consideration. All right? So here we go. To set the molarity of aluminum ion equal to the molarity of sulfate ion for this system, what must I do? I must multiply this molarity by 3 and this molarity by 2, which means that the charge sum for this system is how much? You want to see what's behind my hand? $1. Right? Hey, the sulfate ion is 0.30 molarity. Twice that is 0.60. It's not difficult. Really? Not difficult. So, in preparation for our continuation and discussion of this very important consideration, this charge balance consideration. At the start of our next gathering, I will ask the following: that you write the charge balance equation for this system, which contains all charge species, that's the complete CB. Set that equal to charge sum, and tell me, after you've written this complete charge balance expression, which species could legitimately have their formulas removed from the charge balance equation because numerically they'd be so damn tiny they wouldn't mean anything. But if in addition to this we ask you to calculate the hydronium ion concentration,
You have to use the beam.
what species would have to be retained in this charge balance equation? Pick it up from this point next time.